Hello, welcome. This is the seventh in a series, and it turns out the last in a series of events to try to introduce new faculty members in the SCS to the community. And I'm Scott Hudson. I'm a professor in the HCI Institute. And I'm going to moderate today. And we have two new faculty, both in the HCI Institute for today. First, we're going to hear from David Lindlbauer. David finished his PhD from the University or Technical University of Berlin a few years back, and is just finishing up a postdoc at ETH Zurich for the last couple of years. And in fact, we overlapped a little bit there. I was there on sabbatical. And his interests are in I always wondered whether I should say like virtualized augmented reality or augmented virtual reality, but I think the right thing is mixed reality, right?
All of them are good.
All of those, yes. Okay, and we will also today hear from Alexandra Ion, also now a new assistant professor in the HCI. Alex finished her PhD at the Hasso-Plattner Institute at the University of Potsdam. What is it now, 2 years ago, I think, about, and again, also did a short postdoc at ETH Zurich. So we were all there at least for a short while. They were there longer than I was. And I think and Alex's interests are in computational fabrication, and particularly she's done a bunch of stuff in metamaterials. And both of them will be presenting a recorded video here that tells you a bit about their work. And I think with that, I will go ahead and start off with David first.
Hi, my name is David Lindlbauer, and I'm an assistant professor at CMU's Human-Computer Interaction Institute. My research is motivated by one main observation. If we look at the digital world, it is fully controllable. We can effortlessly perform changes such as in color, texture, or even shape. This is what the digital world is meant to do. Having the same level of control in the physical world, however, is nearly impossible. So my research is motivated by three main questions. How can we bring more virtual into the physical world? What can we do if we had a fully controllable physical world? And how can we balance the virtual and physical world? In order to answer the first question, how can we bring more virtual into the physical world, I create new types of enabling technologies. For example, I created devices from smart materials that change their shape purely optically, and thus allowing the users and system to communicate. I also augmented devices through external devices such as projection mapping. And also I created new types of augmentations by modifying the environment around a target object, like here, the glass. However, if we look at those enabling technologies and other tech such as virtual reality, we notice that there's a gap in between those two. And I'm interested in, if we close this gap, how does this influence human perception? And what kind of applications would this enable? Here's one example of an approach that I created that closes this gap. It's called remixed reality. The user is wearing a virtual reality headset, and what they're seeing is not the pure environment, but actually a live 3D reconstruction of the room. What this means is that they can move in the room freely, but still we can fully control the geometry in the room, enable applications like here, I'm cloning a person in VR, obviously. But this has very interesting applications, for example, in telepresence, maintenance, or education. The last question I'm very interested in is, what would happen if we had a technology that can display anything, anywhere? And I believe mixed reality is a contender here. However, I would argue that mixed reality is inherently context sensitive. The environment changes constantly, once the digital world is no longer bound to the flat displays of our computer screens or phones, and therefore any kind of user interfaces has to adapt in a context-sensitive manner as well. So I'm interested in how is mixed reality perceived by users, and in terms of visual perception skills and cognition, what are the influencing factors, and how can we model those factors? And if we know that, we can build computational tools to build smarter, more context-sensitive user interfaces and approaches for mixed reality. So one example I created here is where we use combinatorial optimization to change when, where, and how to display virtual elements in an AR setup based on users' current context, meaning their task and their cognitive load. And also we started into looking at visual salience and visual attention to make these smarter interfaces for mixed reality that enable a more beneficial user experience. Besides this three-step approach where I use perception to understand more about mixed reality and build computational tools, I believe that a very interesting area of research is also to use mixed reality to gain insights into human perception skills and cognition. This enables a very diverse set of application areas, for example, in health, where we started using virtual reality to investigate balance disorders. So in summary, I'm working at the intersection of perception, computational tools, and mixed reality. For example, in application areas such as productivity, ubiquitous information, in situ and remote collaboration, telepresence, and health, and making sure that we're not stuck in front of our 2D screens for another 30 years. Thank you.
Hi everyone, my name is Alexandra Ion. I'm an assistant professor at HCII and I'm directing the Interactive Structures Lab. So we work in the areas of digital fabrication and engineering advanced materials. Let me give you an example. So we can engineer materials by designing the geometry of their cell structure. Here you see it's only a circular cutout. While in this example, it's really just a bunch of holes, it still creates an unusual material property. So as it is being compressed, conventional materials would actually expand in the opposite direction. This one clearly does not. It does the opposite and contract. So this is highly unusual, and this is to show that even with a very simple geometry, you can create materials that have very unusual properties. So what other fantastic materials are possible? To find that out, we take a very different point of view in our research. So while these so-called metamaterials are traditionally understood as materials, we really think of them as devices. So our long-term vision is to design material structures that act like devices that can receive input, process that input in order to produce output, and all of that within one material structure. And that's what I like to call metamaterial devices. So to achieve this, we contribute novel cell designs that enable novel functionality, and also we develop design tools to assist users creating them. I already looked at the potential of these materials, and I'll give you just a couple of examples. For example, analog processing materials. So here's one example of such really mechanisms. It's a door latch that can be printed in one piece. So it transforms the input of pushing the handle down into the latch moving inwards movement. We've also implemented an editor that includes a finite element analysis to allow users to iterate over their designs quickly. Well, designing such metamaterials is still very hard. So as a next step, we built computational design tools where we dug deeper into the structures to understand their underlying mechanisms and to automate the design for the user. So here we really look at optimization problems, and in this case, it's combinatorial optimization. So as we know, analog devices suffer from signal decay. And to avoid that, we created digital materials where here's an example where we built a door lag that evaluates the user input code, and only if that code was correct, the signal travels all the way up and the bolts are retracted and the door can be opened. All of that built into the material structure. And we also investigated gates, including the NAND gate. Lastly, I want to show how we create output with such materials. For example, we use textures that users can transition through and thereby set their objects, in this case, the shoe sole, to the context, the weather, for example. On a higher level, such metamaterials allow us to add functionality to materials, yet they are lightweight due to their porosity. They're sustainable because we use only a single material. They miniaturize very well because they don't need assembly, and their lifetime can be defined better and foreseen when they will break. So what will we do in the future? In the future, there are many parts still to investigate, such as designing sensor cells that react to the environment, and also to reconfigure cells that reconfigure the material for multifunctional materials. Let me give you two examples. So we could create, with the reconfiguration, we could create mechanical displays or non-volatile information storage, for example. And by adding sensor cells, we could even think of, for example, fences that adapt their permeability based on sunlight, or drywall that switches between cooling and heating. So to get to such advanced materials, we need to research design tools that allow efficient computational exploration of this virtually infinite design space of metamaterials. And at the same time, we investigate novel material structures, fabrication methods, and applications to make such devices a reality soon. And importantly, the design tools and the novel structures will inform each other. Such materials have various application areas, including prosthetics, medical implants, or soft robotics, and are highly interdisciplinary. So very briefly about me. Hi, I'm Alex. I started in January at HCII. Before that, I was a postdoc at ETH Zurich in a computer graphics lab, and I did my PhD at the Hasso-Plattner Institute in Germany in HCI. So a couple of human things about me. I like concerts, sessions, particularly experimental jazz. I love singing, and I used to play volleyball when I was a little younger. So this is the brief overview of our research at the Interactive Structures Lab, and shoot me an email if you're interested in joining the lab.
All right, great, thank you. We all don't have a chance to really clap in this environment, but I think we can all virtually clap. I should have said so at the beginning, but we have lots of time available, and we really want to spend a lot of this session on questions, and you can enter your questions in the Q&A section of the webinar. All right, well, let me get things started there. Let me ask David a question first. I think one question I would ask is, are you considering any particular application areas to take up next? Seems like there are many, many applications of this. Are there any particular ones you're excited about?
Sure, thanks for the question, Scott. So I think there are two main application areas I'm currently most excited about. One is I started a collaboration with a critical care clinician from UPMC, where we look at the potential of using advanced remote interactions, such as augmented or virtual reality, for simulation and training of ECMO devices. So ECMO devices are essentially artificial lungs, and the training happens kind of as a trainer flies over to Arkansas, or you pick a hospital somewhere in the country. They spend 4 days there, they fly back, and they rinse and repeat that every weekend. So this is a process that doesn't scale, and I'm interested in how could we scale this process more so that they don't have to travel, and we can improve the experience of the training for these high-end devices while kind of making it more sustainable. So that's the health part I'm very interested in. The other part I'm very interested in is casual interactions, more or less. So what would it mean and what would it take for us to replace our predominant devices such as phones? Currently, all the information we get are 2D displays. It's somewhat boring and limited. In particular, if we see that we are visually dominant creatures and everything we look at all day long are flat screens. So how can we improve that, and what would it take? And what are really the implications in human behavior and human cognition if we were to replace all the interactions we do with our phone with a headset that could potentially show virtual contents anywhere and at any time in 3D? And this will involve computational approaches just because of the context awareness I hinted at the video.
Okay, great. Okay, we do have a question from the audience. Katie asks, how can alumni get involved in and support your work? I think that's actually a question for both of you. Alex, go ahead.
Yeah, great question. Well, I mentioned in the video that there are like different application areas and research direction where these materials can lead, and I've already started a couple of those. For example, going into prosthetics in that area. So there are like a bunch of things that we're looking at, for example, to making these type of materials cuttable. So you have these paper strips, for example, and by folding them up, they're kind of like getting really, you can vary the elasticity, which means, you could cut them at home just with scissors and get like a kind of material properties out. They're good for education, things like that. And then also, well, as I mentioned, we're looking into making prosthetics, ankle prosthetics out of these because they're highly customizable and you can ship them flat. So these are just a couple of examples of the different directions, but this is like one example that if this is something that you find practical or goes in the direction that you're interested in, then just shoot me an email. You've seen in the video that there are like a bunch of application areas and research directions that this could go in, and I'm very interested in kind of expanding on this view even more so. So yeah, best shoot me an email and we'll get in touch and see where our mutual interests lie.
So, I mean, I can only echo what Alex said. I think having particular applications or interests, the lab is working on a variety of projects. And if there's a specific application area where you think that our expertise in understanding perception and understanding novel devices can help, I would be very open to it would be fantastic to chat. This is also how this collaboration with UPMC started, with a single email. It's like, hey, would you be interested? The other part I would personally like to build is to bring in these new types of devices and really computing paradigms more into an educational context at CMU. So I'm in discussion with folks from the Ideate Center, for example, on how we can improve the education also for students by bringing in these devices. I think that for a lot of, if you think about interaction design, usability, but also user-facing systems, software developers, and really anyone who's in contact with technology and users should be aware and should be educated in how to operate and how these new devices, new paradigms work. So I would be very interested also to talk here more about the educational aspect at CMU, and maybe, I don't know, I would like CMU to be one of the hubs for 3D interactions. And for that, we need to build something larger, maybe kind of building more lab spaces and building a place where students can go in their free time and work on the technologies. And I think this is something I would be very interested in building up a more of a competence center here.
All right, Great. Let me ask a question of Alex this time. Let's see. So, Alex, why would you characterize metamaterials as having benefits over sort of traditional mechanisms and particular traditional ways of manufacturing mechanisms?
Yeah, that's a good question. So I think it's not really necessarily a replacement. Traditional mechanisms make sense in specific contexts, but there are some benefits that I think I alluded to. So there's, for example, you don't have a problem with lubrication and friction, which makes traditional mechanisms break at some point if they catch dirt, and then it kind of like the multiple parts rub against each other. Then these compliant mechanisms that are made from one piece, they're well, you can miniaturize them very well, which gives them a lot of importance also in medical fields. There are stents, for example, that have been like rather simple ones, but cylindrical ones that can unfold in this like multiple dimensions, and that is only possible because they're made from one piece and they only work by kind of deforming the actual material and structure. So there are like a couple of benefits there, and that it's a different context where these operate in, and I think that this context is rather new anyways, and requires way more exploration. And one thing that I always like to think of is that many of these properties have been discovered almost by accident. So that is something that, so for example, this auxetic property where you pull in one direction and it expands in two directions, that's highly unusual. But I think the HCI aspect is lacking in this, in this discipline that stems from engineering, and giving people more tools at hand to explore these spaces efficiently will also propel the field forward to finding out about new, what else is there, what are all the benefits that these materials can have. Right now we know a couple, but there might be more, and the first ones are already so promising that I think it's worth exploring more.
Okay, well, let me follow that up with another question for you, which is, what do you see as sort of the big barrier to this sort of becoming widespread and just working better? What is it that needs to be overcome?
Yeah, there are a couple of things I would say. Well, particularly two essentially. It's the fabrication technology. That's and then the exploration part that I already mentioned, like you can design any geometry you like. So how do you know which geometries to combine that give you in combination a new a new material that can do things that traditional materials can't do, like they're essentially create smart materials, right? So that is kind of the part that I mentioned earlier, that we would create exploration tools that automate some of the geometrical parts, because they're hard to do for a human, but then like the overall exploration part should be very well in the control of the human, to leverage the intuition of experts, but also the creativity of many. And why shouldn't everyone contribute to kind of like exploring this design space? So, and then the second part is the fabrication technology, which is traditionally these things have been 3D printed, because the idea is that you have like complex structures that do something smart, right? But also the question that I had during the work, which is why many of the materials look simple, like the individual cells are simple, but then together they do something smarter, is to kind of take not be so dependent on 3D printing technology making a big leap, but really looking at simpler structures that can still do interesting things. And then one of the latest steps in that direction is actually these type of structures that can actually be laser cut or cut in with whatever essentially, but they're just like flattenable. They can be cut. They also work in 3D. So kind of these directions. So those are the two main obstacles that I see and that we're tackling.
All right, great. Well, let me ask a similar but not exactly the same question for David, which is, what do you see as sort of the most challenging thing in front of you, but that you're intending to work on soon?
It's a nice twist to the question, Scott. So when we use our phones, everything is pretty clear from a interaction software development point of view. So everything is on the screen, and right, the user kind of, maybe I'll hold it in front of me, kind of, or on top or whatever. But everything is reasonably well defined. If you use a desktop computer like I do currently, I have one window on this side and then another one in front of me. And as a software developer, I can rely on the fact that my content is displayed where I'm also developing it. And this will no longer hold true, I think, for future applications. Software developers, designers, really content creators, will develop an application somewhere, but they don't know how it's going to be used, where it's going to be used, and what the context is in which it is used. So if I have a map application, for example, that's currently on my phone, it's a screen, right? I might turn on and off navigation instructions, but it's pretty much the same everywhere. If I'm now taking the same thing in a new type of technology, where I have a headset, I have maybe 10 years ahead or 15 years ahead of lenses, some of this is more integrated. I can show navigation instructions as a map in front of me in a blocking manner. I can put arrows on the street. I might have more subtle ways to display those contents. So I have this dimension of how do I show it, and then I have the other dimension of when do I show it. If a person is walking, I don't know, on a kind of in the street where there are no cars and everything is reasonably safe, I can use a lot of their kind of essentially attention. If that same person is walking somewhere in New York and you have pedestrians that are crossing kind of your way and that are bumping into you, you have cars, you have all other things, an application needs to adapt to this. Otherwise, it's really becoming hazardous, and it's really not as useful, even though it might show the same information. So I think for AR or mixed reality to become kind of to overcome this challenge, I think that, so the point is, the main challenge I think here is that the context is unknown to where a user operates, and that it's impossible for content creators to predict and to design for all those contexts. That's something my lab is also working on heavily, where we say, if we had information about the context here, so we measure, for example, people's load, cognitive load, or we take the information we get from a computer vision system, we use this to adapt, create, and generate user interfaces on the fly for a particular scenario, really personalized also. This is, I think, one of the key challenges in terms of software that I'm working on. Hardware is a completely different beast, where people fight against optics and physics, but that's nothing the lab is currently involved. But I think those are the two main parts. Not unlike Alex, it's the hardware that is hard and the software that is hard. So there's definitely some parallels there.
Okay, good answer. So we have a question from the audience for both of you. Do you see your work being part of accessibility efforts for people with disabilities? Have you done anything in that space?
Yeah, so it's actually something that we're doing right now. As I mentioned, looking at kind of creating prosthetics. In this case, we're looking at lower limb prosthetics and ankles for using these types of simple ruffle structures. Now, the cool thing is that you can just unfold them and send them to the user in an unfolded state. You can highly change their spring stiffness, essentially, because the ankle is typically modeled just as a damper and a big spring. So you can adapt that to the person really easily, and then send out this highly customized prosthetic that could serve typically underserved communities. It would be very cheap to make. And then one big advantage is also that the weight distribution, because these structures also lightweight, is advantageous compared to traditional, like current state-of-the-art ankles. They have heavy load, but in terms of distribution, the overall load is somewhat similar to a healthy limb, but the weight distribution is at the ankle, which over time causes damage in hip joints and other joints. So that is something where we're looking at these types of structures that likely fulfill these the requirements and even have some more benefits, like we can add, for example, lateral movement that are typically not added to prosthetics. We could make them reconfigurable so that you have like a couple of settings that are specific to you. As you walk on the pavement is very different than walking on some uneven terrains, like taking a walk in the forest, something like that. So this is kind of like the area that we're exploring right now. And and we can integrate sensing throughout the whole prosthetic with these we call them ruffles, because it's essentially just bend sensors. And that is also something that in the biomechanics community, they don't have that information, because it's also deemed not important, but we can generate that knowledge really easily just by having these structures, being the way they are. So that's kind of one example where we're looking at right now.
So what my lab is doing is less physical than what Alex is doing. So how I think about accessibility a lot has to do with visual processing. So for example, any kind of AR or mixed reality technology could potentially be used to for people who have visual disability, for example. The simple example being kind of color blindness. First, we can use the technology to guide users' attention towards maybe visual features that they might have missed. And the lab is currently working on predicting really when will users notice certain types of information. And the other thing I think is very important for us is that because we're developing this new technology, that we include accessibility really as a first-class citizen here in the whole development. So that it's for a lot of technologies that we're currently using, accessibility has been, or at least feels like an afterthought. And if we now design a new computing paradigm, we have a chance to change that. One aspect that has frustrated me quite a bit is I've been involved in organizing a virtual conference last year, and we were looking at solutions for holding a virtual conference. And it's the same thing. Accessibility is for a lot of companies an afterthought. It's not considered, or kind of maybe in the medium term once we hit our user numbers. So a lot of technologies that we looked at, we had to discard immediately because it wasn't considered. So I think if we look at remote technologies, and this is something that the lab is working on, where we look at, okay, how does video conferencing, what does the future of remote collaboration, remote work look? We definitely do consider this as an important aspect, especially for remote, where we say, okay, suddenly one of the benefits of a virtual conference, for example, is that there is no cost of travel. The cost of registration can be very low. So suddenly we can be involved in we can give out what we did for the WIST conference, for example, free global self-registrations. However, bandwidth, sudden internet bandwidth, it's nice if you give people free registration. If the internet is down, it's down. And the question is, and not everyone has the same bandwidth, for example. So how do we account for that? So accessibility in a health context, but also in the broadening participation context, I think is very important, where I'm working on a technology that's potentially hungry for bandwidth and for visual quality, just because it's hard to transmit the reality across the wire or Wi-Fi signal. So the question is, what are different levels, and really how good of an experience can you deliver within certain constraints that you're having? And this is something that we actively consider also here in a project currently with one of the students, where we look at what is the resolution, for example, if you look at a 3D mesh of a face, what is the resolution required in terms of vertices, faces, and edges, so that people can still, for example, recognize facial expressions. And this has interesting implications for compression, for example, and how we can handle this. So I think a lot should and has to be involved directly when we build these new technologies. And this is what we're involved in.
All right. Let's see, what am I? Oh, yes. Let me ask David another question here. If we don't have an audience question, I don't see one yet. And it's actually a question from me that I want answered. So not a general question, but what are your thoughts? So most of what you've done in the mixed reality side of your work has really been in sort of the visual domain. Do you have any plans? Do you have any thoughts about integration of haptics? That is, some ability to actually feel things. And this sort of came to my mind when you were talking about remote. That's one of the things that seems still incredibly hard to do remotely. But anyway, what do you think?
It's a great question, Scott. I've been collaborating with people on haptics. I think, as I said, right, we are visually dominant, and this is also my personal pet or something I'm currently focused on. I do think that there's very few that enhances the realism of a virtual environment than if you put on a VR headset and then you go somewhere in the virtual space, you sit down, touch a table, and both sensations are actually reproduced. Because, for example, you have a passive proxy like an actual chair and an actual table. This boosts your present and immersion so drastically that we need to consider this, especially if we're in a virtual reality context. For mixed reality, I think there are two parts that I think are interesting. One is, how can we leverage existing physical objects that are already there and then visually modify them so that if I touch our tactile sense has a lower resolution than our visual sense. And how can we really leverage this by saying, okay, I'm visually augmenting something that's actually there, and then I touch it and it has the same realism. That's the one part. The other thing I think where haptics is very interesting is for novel input devices. Input in AR and VR is still hard, right? Joysticks and whatever are somewhat or keyboards don't really translate because they lack the third dimension. And my postdoc, what we've been working on, for example, is with a PhD student at ETH, Thomas Langerak, and the people I've worked with, Otmar Hillegas and Christian Holtz there. We looked at magnetic input devices, for electromagnetic that can attract and repel objects, which allows for very nice three-dimensional input and output, and for really a new class of input devices that might not be really the way to go for casual end users, but they're really great for specialty applications such as simulation and surgery, maintenance, pilot training, It's really these control contexts where it doesn't matter if a device is $1,000 or $10,000 because you require the precision. I don't even know how much a flight simulator costs, but the cost of adding a $5,000 device to probably something that's multiple $100,000, but it still gives you such a push is incredibly powerful, I think. So I think it's very important.
All right. All right, let me go back to Alex here and sort of re-asked a question here of like, what application areas do you think are going to be interesting as some of the most interesting things you're intending to do relatively soon or in the near midterm?
Yeah. Well, so some things that I'm looking at now and soon is, I guess, goes more in the soft robotics side, where you have these materials that can be, they can be robots at the same time, so they can change, I don't know, they can change their material properties, such as how bouncy they are. If they, maybe you have a robot that should walk somewhere and then, catch something that falls or something like that. So you can have like this material that can be a robot to walk and crawl, and then switch over to it being a material and kind of damp the impact of something falling or something like that. So this is kind of like a general area of combining robotics and materials and bringing them closer together, as opposed to having materials just being kind of like the structural part of a robot, the stiff part, the limbs, the robotic limbs that move. That is one area that I'm interested in right now. And then the second one is, as I explained earlier, the whole idea of prosthetics, getting them, to be cheap and easy to make, and really accessible for everyone, and still be of really high quality, and thereby contribute to a higher quality of life. So these are I think the more concrete things that I'm most interested in right now, and then there are adjacent fields that are also may not look the same, but like if the structure is kind of similar, like deployable structures where you have complex shells that can unfold, like by having just a very simple actuation mechanism, they can unfold into something more complicated. And there, you can think of disaster areas and having deployable shelters there. You can even think about more advanced applications like unfolding unfolding things in space, for example. So having like a simple actuation means that you save loads as you transport something on a rocket, but still you get like more functionality in how this thing unfolds, essentially, because you integrate that into the material rather than into the actuation as we traditionally do right now. So this is kind of like a more abstract way of thinking of these types of materials, but that is really what it is, that like you design a geometry using computational algorithms that we're working on to embed more intelligence, if you so will, into the material structure itself, rather than kind of having that in many and complex actuators on the outside.
All right. Getting close to the end of time here, but I will ask one more question here. Let's switch back to David for a second. I ask you, what's the hardest thing you're planning on working on soon? What's the coolest thing you're going to work on soon?
Do they need to be two distinct things?
No, I guess they don't, but.
So I think the hardest thing is that we're close to the human, and humans have the annoying feature of being very unpredictable, and having if we would like to do something that generalizes, for example, a simple example of how should our layout in 3D look like, we can't, if we ask 10 people, we will get 12 different answers. That is and remains somewhat of the hardest part, that creating generalized guidelines doesn't really work. So we work on somewhat that generalizes underlying in a computational tool, but is hyper personalized by taking into account really all the historic data we have from someone. That all sounds nice, which brings to the second hard part is we can't run longitudinal studies. We really can't run any studies like we do on a traditional computer, just because the hardware isn't ready, and whatever we do is somewhat confounded with the fact that we have suboptimal devices. So either devices with a small field of view, or they're heavy, or they have a low resolution. So we constantly, and to paraphrase Buxton, try to do smart things with stupid technology. And this is among the kind of the hard parts that is really our day-to-day business also. The stuff that excites me currently most, and I'm not sure if that is the coolest part, is there are two things. One is the collaboration with UPMC that I mentioned, where we use kind of VR to have very immediate impact on ECMO training, where we are looking into something where we create some foundational knowledge, but also something that could be deployed and should be deployed soon, because there's a need for these devices, and this was even more apparent now during the pandemic. The second is a collaboration I'm hoping, or a kind of work that I'm hoping to start soon, is where we use, and just to kind of, for ECMO, what I said earlier, just in case people don't remember, is these artificial lung devices that are essentially outside of the body, and there are a lot of tubes in someone. This is really for a critical care situation, an emergency situation, where we use VR for the training here of doctors. And the second part I'm excited about is the potential of using the technology that I showed in the video remix reality for behavioral and cognitive psychology experiments, where we try to use it to find out more about human memory, for example, and trying to overcome the gap between 2D stimuli that psychology typically uses that are very controlled, and real life experiment where we have a lot of ecological validity. So those are real life situations, but are really hard to measure, and we're hoping to bridge those two. So those are among the coolest thing that I currently can think of.
Okay, great. So we're pretty much at time here. I want to thank our panelists, Alex and David, as well as our audience and participants here. Everybody should know that you probably know from the beginning that this was recorded. This is going to be available on YouTube if you want to pass it to others fairly soon after it gets captioned and processed and so forth. And with that, I think we'll draw to a close for today, and thank everybody for attending. And we hope to see you. Actually, I think we all hope to see everybody on campus sometime soon, maybe in the fall. All right, bye-bye.
Thank you, bye.